doing my homework 3 video. Yeah, it's homework 3. So before that, I will show my work. For this video, the voice is gonna be a bit lower since it's kind of late in the night. This is the equation sheet, and this is the problem statement that I will use. Now I'll get to the point. So starting from the beginning, we know that L equals 2.00 meter, and the thickness, let's call it tau, is 1.00 micrometer. The delta y is 4.8 centimeter. Now, since we can see that the single slit and double slit has a overlapping place in terms of its dark fringe, we can set up these two equations. So for single, it's see it over here. For dark fringes, this is the equation for single, and this is the equation for double. And as for 1 and 4, the way I got it is I counted I essentially just counted which dark fringe it is. This is the first one. For the single, it start off from 1, and it's the first one. So we count 1, and this will be m equals to 1. For the double one, this one's a bit hard, but we gotta zoom in. Starting from the middle, it's 1, 2, 3, 4, 5. It's the 5th one, and we start counting at 0, so it would yield us n equals to 4. This is actually put out of ink, and I will get a new one. And with these two equations set up, we can move stuff to the other side, and it eventually gave us that equation we get. And recalling from the graph, it says at the double slit, 250 micrometer is the length between the top edge of the first slit and bottom edge of the second slit. This would give us that 250 micrometer is D plus A, with D being the distance between the center of the two slit in the second figure. Now we cancel our lambda from the equation over here and move stuff to the other side. We will then get D equals to n plus 2 half of A, which gives us 250 micrometer equals to 5 plus half A, and this would give us 250 micrometer equals to 11 divided by 2A, which would eventually become that. You can see the secret is over here. It's a bit of mathematical operation, and we'll be able to get the width of the slit A. This applies for both over here, since it says both slits in the double slit situation has the same width. With the width in line, we could start furthering the calculation to get the refraction index. Now, we know that A sine theta equals to lambda, and this is given from the single slit dark fringe equation we set it up. We also know sine theta is it can be getting from this. It's a single trigonomic, with this being the starting point in the single slits, right? And this being the central point up here, so it's half of delta y divided by the adjacent side L. Just because the difference between the adjacent side and this side is so large that we can effectively treat adjacent equal to the hypotenuse. Thus, with that in hand, we can say A times delta y divided by 2L equals to lambda, and plugging in everything we have above, get lambda equals to 500 micrometer divided by 11 times 4 times 0, 0 m times 2.4 cm, and factoring a lot of things out, we will get 500 micrometer divided by 11 times 0.024 m divided by 4m. Remember, only converts everything on the top of, okay, remember to convert delta y into meter, but don't convert the metric of 500 micrometer, because for that part it's not going to be cancelled out. Leaving it as is will make calculation easier. Oh, sorry, okay. I accidentally put one more step in. So, yep. It equals 0.54. This will be the lambda. After some basic mathematical function. Now with the lambda in hand, we can move to another equation I haven't quite set up yet, but the phase difference can be gotten in this case with 2 pi divided by tau divided by minus tau divided by lambda. This is the equation we'll use to calculate the final refraction index. Actually, I need to explain a bit more here. With this equation, it becomes simpler. Now, you can see that I didn't really mention the changing, or like the phase shift there is, because in this case it's finding the difference, and the initial phase shift is pertained with the changes happening to the phase difference. That part wouldn't matter, sorry. Moving to the right. Now, knowing this, we could say that now, with a normal double slit interference graph, right, in the middle, it has a light fringe, which means in the middle, it has the phase difference in n times 2 pi. And this is normal. But in this case, we have a dark fringe in the middle. I don't know if you can see it. Let me see if I can. Yep, like in the corresponding part. So there's a dark fringe, which means that over here, it must be in the form of 2n plus 1 pi. And here n must be greater or equal to 0. Setting up both sides of the equation just so calculation become easier. Canceling stuff out on both sides. This is the equation we will use to find the lowest number for n. Now, okay, it's a bit confusing. I'm gonna change the. Yeah, I can't quite find a good sign for it, but the n on the left hand, which we're finding, is the n for the refraction index here. I'll change it to m. Let's make everything easier. Like now it's in the m form. Anyway, here set m equals to 0. It would give us the lowest n possible, which would be n equals to lambda divided by 2 tau plus 1. And since lambda divided by 2 tau must be a positive number, it's at least greater than 1, which would make sense. We know that lambda is 0.545 in terms of micrometer divided by 2, and tau is 1 micrometer, which it is very convenient. This will give us 0.2725 plus 1, which is 1.273. Here we have it, our final result. And that'll be it for my video.